Un gusto tenerlos acá con nosotros. Y ya, pues vamos a poder dar inicio a nuestro workshop. Es un gusto tenerlos. Ese workshop se hace en el marco de la cooperación entre Perú y Alemania. Perú y Alemania en el 2014 han firmado un convenio de cooperación en temas de minería, tecnología, formación, medio ambiente en esas áreas. Y desde 2015 en la Cámara Alemana tenemos el Centro de Negocios Mineros, donde ya vamos haciendo eventos, actividades, apoyo a ambos lados, a Perú y a Alemania, en todo lo relacionado con la minería. Me da mucho gusto hoy día tener nuestros partners, nuestros aliados con nosotros desde el proyecto MinSuS de la BGR, el Servicio Geológico Alemán, y la cooperación alemana. Achim Konstantin está con nosotros, quien va a moderar luego las preguntas y la discusión. Y de la empresa Wismut tenemos a los tres expositores que Achim nos va a presentar. También me da mucho gusto tener con nosotros al director general de minería, el ingeniero Alfredo Rodríguez, que nos va luego a brindar unas breves palabras también antes de que empiecen los expertos alemanes. Solo por tema de logística, tenemos traducción en simultáneo. Ven abajo el símbolo de un globo donde pueden escoger el idioma castellano para poder escuchar la traducción simultánea. Para las preguntas les pedimos que por favor utilicen el chat. Ya durante la presentación pueden hacer las preguntas, las voy a recopilar y al final vamos a hacer las preguntas hacia el respectivo ponente. Ya, Achim, entonces te doy la palabra y ya luego al director general Alfredo Rodríguez.
Muchas gracias, Jan Patrick. Buenos días con todos, o buenas tardes para los colegas que estén en Alemania. Gracias por la perfecta introducción, Jan Patrick. Para repetir, mi nombre es Achim Konstantin. Yo trabajo para el Instituto Federal de Geociencias y Recursos Naturales de Alemania, la BGR por sus siglas en alemán. Y somos el Servicio Geológico de Alemania. En ese sentido, digamos, somos el homólogo de INGEMET en Perú. Tengo el agrado de guiarles hoy día por este seminario, y para no perder más tiempo, quiero iniciar a presentarles nuestro primer panelista, el señor Óscar Alfredo Rodríguez Núñez. El señor Rodríguez es director general de minería del Ministerio de Minas de Perú. El señor Alfredo Rodríguez es ingeniero de minas, graduado por la Pontificia Universidad Católica del Perú, con más de 30 años de experiencia en el sector público y el sector privado, en operaciones mineras y en el desarrollo de proyectos mineros. Y entre los años 2007 y 2009 se desempeñó como director general de minería y director general de asuntos ambientales mineros, siendo responsable de la gestión administrativa de dichas direcciones y de los procedimientos a cargo, como las autorizaciones para el desarrollo de la actividad minera, la promoción de la actividad minera y las certificaciones ambientales correspondientes. Asimismo, entre los años 2003 y 2006, se desempeñó como director de fiscalización minera y director de promoción y desarrollo de las actividades mineras. En el sector privado, y durante los últimos 8 años, se desempeñó como ingeniero senior en la consultora SRK Consulting Perú, como responsable del área de permisos, habiendo procurado la aprobación para diversos proyectos mineros. Asimismo, fue gerente de operaciones en la empresa AHK Perú, sucursal de Perú, empresa dedicada a la exploración y búsqueda de proyectos mineros. Y un gusto tenerte acá con nosotros, Alfredo, y te doy la palabra para tu exposición. Muchas gracias.
Bueno, muchas gracias por la bienvenida y, bueno, agradecerles y felicitarlos por la convocatoria a este workshop para tratar temas de uranio, que es un tema que está ahorita en bastante discusión en el país. No tenemos una explotación de uranio y sería nuestra primera experiencia, tanto operativa como legislativa, por parte de nuestro país. Sin embargo, tampoco tenemos, de manifestar que tampoco tenemos términos de referencias, los cuales ya estamos trabajando con IPEN para poder trabajar este tipo de minería. Hay que recalcar de que la minería de uranio no requiere una legislación especial, no requiere, digamos, el establecimiento de normas diferentes en relación al sistema de explotación. Lo único que requiere son términos de referencias adecuados para poder hacer los trabajos de forma conveniente en beneficio y el resguardo de la salud y el resguardo del medio ambiente. Los procedimientos serían como cualquier otro, ya que el aprovechamiento de las sustancias del aire, minerales del suelo y del subsuelo y del dominio marítimo se encuentran regulados ya por la Ley General de Minería. El uranio es, por ende, un mineral que se encuentra bajo el amparo de dicha ley, no se requiere normas técnicas con rango de ley para la exploración y explotación. Ya tenemos las normas reglamentarias aplicables a la actividad minera, y como manifesté, el Ministerio de Higiene y Minas, coordinación con IPEN, está trabajando las normas técnicas adecuadas que permitan elaborar los estudios de impacto ambiental, la explotación, la labor general de beneficio y el almacenamiento de minerales radioactivos. El uso de fuentes de radiación ionizante en general. Está a cargo de la Oficina Técnica de la Operación Nacional, es la OTAN, de la Oficina Técnica de la Autoridad Nacional del IPEN, ¿no? Ahora, tenemos un yacimiento de litio uranio ubicado en la zona de Puno, que es de conocimiento de todos ustedes. Dicho yacimiento va a demorar bastante ser explotado, ya que no tiene recursos, no tiene reservas, solo se han detectado recursos, con lo cual tienen que comenzar a hacer exploraciones más amplias, y para eso tendría que pedir los permisos y definir la forma como va a ser trabajado este yacimiento en la exploración y posteriormente en la explotación. Hay que tener en cuenta también que el yacimiento de litio se ubica debajo del yacimiento de uranio, es decir, va a requerir la explotación del yacimiento de uranio para la explotación de litio. La exploración de litio tampoco tiene reservas, no tiene recursos, no tiene reservas determinadas por la empresa a la fecha, y la explotación de litio conlleva pues la remoción de previa del yacimiento de uranio que se encuentra subyacente en la capa superior. Esto generaría la liberación de elementos radioactivos, materiales ionizantes al ambiente, suelo y agua. Además, tener en cuenta que las garantías financieras para el plan de cierre serían bastante onerosas en relación a otro tipo de minería, ¿no? De todas maneras, les agradezco la invitación para este interesante workshop que va a ser de conocimiento tanto del sector público como el privado, la forma de explotación, los beneficios y las dificultades intrínsecas que conllevan a este tipo de explotación de los yacimientos uráneos. Muchas gracias.
Gracias a ti, Alberto. Muchas gracias por darnos ese contexto peruano. Y bueno, entonces, para no perder más tiempo, quiero dar la palabra al doctor Robert Seeland, nuestro primer panelista. El doctor Seeland estudió geoecología en la Universidad Técnica de Minas de Freiberg, en Alemania. Cuenta con un doctorado en el campo de la hidrogeología. Ha hecho investigaciones hidráulicas del salar del Uyuni en Bolivia. Y desde el año 2014 hasta el año 2019 fue gerente de materia de modelado en la empresa Wismut, que ha sido un antiguo gran productor de uranio, y desde el año 1991 la empresa Wismut está a cargo de la remediación de los pasivos ambientales relacionados a uranio en Alemania. Desde el año 2019 asumió el cargo del asistente del director técnico de la Wismut y cuenta con 10 años de trabajo científico y de ingeniería en el campo de hidrogeología, la geoquímica y el monitoreo ambiental. Entonces, un honor tenerle aquí, y bueno, the stage is yours, Mr. Seeland.
Okay, thank you very much. I will share my presentation. Good afternoon from Germany. Good morning to Peru. Dear ladies and gentlemen, my colleagues, Mr. Schmidt and Mr. Bonico, and I myself, we are very glad to have this opportunity to share with you our experiences and also the lessons learned in more than 30 years of rehabilitation of uranium-related mining sites in Germany. I structured my presentation in two parts. At first, I would like to give you a very brief overview about the entire Wismut environmental rehabilitation project. In the second part, I will focus on the water-related aspects in mine remediation. Finally, I will give you some important conclusions and also lessons learned. Let me start with the historical background of our company, Wismut. After the Second World War in 1946, first exploration and uranium mining started in Germany under the supervision of Soviet military. Between 1947 and 1990, uranium mining and also processing was operated by the Soviet mining company. Later on, it was transferred into the German Soviet stock company, Wismut. Within the wake of the German reunification in 1990, uranium ore mining terminated or was ended. Wismut produced in total 231,000 tons of uranium, which made Wismut to the fourth largest uranium producer in the world. Starting in 1991, dismantling and rehabilitation of the mining legacies was carried out by the present-day remediation company Wismut. More than 40 years of mining and milling of predominantly low-grade ore affected an area of approximately 100 square kilometers in the eastern part of Germany. And what was the price for that? The landscapes were devastated, the environment was polluted, and the infrastructure was damaged. You can see on these pictures the situation in 1991. There were altogether 5 underground mines, 1 huge open pit, and an operational area on together 3,700 hectares. Beside this, more than 300 million cubic meter of waste rock from the underground mine activity was dumped on 48 waste rock dumps. The uranium ore was milled and processed in 2 large processing plants on an area of additional 75,000 hectares. The residuals of the processing step were disposed in large tailings ponds. We have 7 large tailings ponds on an entire area of 570 hectares. They contain about 160 million tons of radioactive contaminated sludge material. In addition to these physical devastations, we had to manage about 30.6 million cubic meter of contaminated mine water each year. And from this resulted 30,000 tons of residues from the water treatment, which we had to manage. Let me show you our sites on this map. We are in the eastern part of Germany, and there are 5 former mining sites. Here we have a sandstone deposit. This one was a coal deposit. The other 2 ones are Wien-type deposits. And in Ronneburg, we had a black shale deposit. Beside the mining sites, there were the 2 former processing plants which were under decommission today. So what were the main remediation goals? The first was to ensure the public safety, especially with regard to the physical and chemical stability of all remaining structures and objects. Additionally, we need to enable a future land use after remediation, for example, for agriculture, forestry, or even for business settlements. Very important from the environmental perspective was the aim to minimize the radiation risks and hazards, which are mainly caused by uranium, but also by radium and radon gas. We need to achieve an individual effective dose for the public of less than 1 millisievert per year. This is the reference level and also the remediation goal. Another aim is to reduce any adverse effects to water resources, such as groundwater and also the surface water bodies, rivers and streams. One non-visible or not obvious challenge was the destigmatization of regions that have been affected by uranium mining. The remediation tasks were deviated from legal regulations as well as from national suggestions. When the so-called Wismut Act became law in 1991, the former Wismut Mining Company was transferred into a remediation company, which is completely owned by the German government. And this company, this present-day company, Wismut, is responsible for the remediation of all the uranium legacies in Germany from historical times. The Federal Mining Act in Germany is the overarching and legally binding document for our activities. Furthermore, Wismut needs to consider regulations regarding radiation protection, groundwater and surface water protection, as well as ground and soil protection ordinances. To give you a number, in the last 30 years, Wismut submitted more than 6,500 applications to the authorities, and we received about 10,000 individual permissions, so that you can have an imagination. Let me come to the main remedial activities after the closure of uranium mining in 1991. It comprised the full scope of remediation, among others, the dismantling of surface structures and buildings, the removal of contaminated material and the safe disposal, then the safekeeping of wastes and residues such as tailings. You can see here a picture of a tailing pond and waste rock dumps, for example, here. A very big challenge was the refilling of the former open pit. We will hear more details from my colleague Ulf Barnekow in the next presentation. And last but not least, the flooding of underground mines was a very big challenge. All these tasks above are or belong to the physical remediation activities, and all these will be finished by 2028. However, there are some additional tasks, such as water treatment, the treatment and disposal of their residues, and the environmental monitoring, which belong to long-term tasks. all these tasks lasts at least until 2050. So this should be a very brief overview of the entire Wismut rehabilitation project. In the second part of my presentation, I want to go in more detail with a special focus on water aspects in mine remediation. As you can see here, water-related aspects can be classified into 3 fields of action. The first one is the characterization of the site hydrology, including the analysis and the understanding of the different chemical and hydraulic processes. It includes the determination of the amounts of contaminants and also the identification of the sources and the potential of different kinds of pollution. In order to understand our systems on site, we need a reliable environmental monitoring. Based on the results of this monitoring, we can deviate, or we can perform certain modeling and make predictions for the future development of, for example, contaminations in groundwater, surface water, or even in ponding waters. So from these model results and predictions, very specific technical measures were deviated, which are used to remediate our sites. Here we can subdivide 2 groups. The first one are the classic water management measures. Here we can we have to mention the flooding of underground mines, the collection of contaminated waters, the water treatment, and finally the discharge of water and the quantity and also quality control. The second column deals with technical measures who regulate the water balance of a certain mining object, for example, of a waste rock dump or of a tailings pond. Here we have to create a surface contour on our object. We have to establish a specific cover system, and we need to concentrate the runoff from precipitation or rainwater. In the following slides, I want to go into more detail to these yellow boxes you have seen. Let me start with the fundamental procedure for safekeeping of underground mines. In the lower part of the slide, you can see a very simple sketch of one of our underground mines. The mine is located in a deep sandstone aquifer, and beside conventional mining in former times, here also leaching technologies were applied. It was very specific leaching, which was applied underground in sandstone blocks. For this, about 1 million cubic meter of sulfuric acid was pumped into sandstone blocks in order to leach the uranium from the deposit. In the result, an extremely high contaminant pollution was formed with pH values between 1 and 2 and uranium concentrations of up to 20 gram per liter, not milligram. So now try to imagine the situation right after the termination of the active mining. If we would stop pumping the water, the mine would be flooded naturally by groundwater inflow, but in an uncontrolled manner. This would lead to an uncontrolled discharge of contamination into other aquifers and even into surface waters. And to avoid this, we need these steps for the remediation of the underground mine. First of all, we disposed or we blocked water-threatening substances in the mine. In the second step, we remediated adits and surface openings, and we had to backfill near-surface mine openings in order to avoid any subsidence on the surface. The main part is the controlled mine flooding. One moment. For this, we had to make sure that the contamination is catched in a controlled area underground, and for this we installed a so-called control drift at the periphery of the reservoir, where we could collect all downstream contaminations from the mine. All this contaminated seepage water and the outflow was pumped to the surface, treated in a water treatment plant, and finally it could be discharged into the river. To enhance the remediation and to decrease the huge contamination potential, in part, cleaned water was re-injected into the mine in order to have a washing effect of the mine. And this circle was run for several years up to today. So, and finally, we could decrease the uranium concentrations from initially 20 gram per liter to right now 10 milligram per liter, which is much lower, but not low enough. And the entire flooding process is accompanied by environmental monitoring to make sure that there is no impact on other aquifers. The second box was about different water collection systems. I would like to show you this aerial picture of our largest uranium or of our largest tailings management facility. Very high contaminations occur in the poor water, and the poor water is infiltrating or penetrating the dam and draining into a local creek. In order to avoid this seepage effect, we installed so-called protection wells in the sandy beaches of our tailings pond. There we pumped out the high contaminated poor water, and due to this pumping we create a depression cone or cone of depression. And due to this depression, the hydraulic gradient, so the pressure difference, decreased between inside the basin and outside, and thus the amount of seepage decreases significantly. In case of underground mines which are flooded, we also have to collect the contaminated mine water. Here are three different types in a sketch. The first one, you have the flooded mine, and we installed a gallery or a kind of horizontal adit through which water can flow directly to the water treatment plant. In the example I mentioned on the slide before, we have pumping wells and we control the flood level in the mine by pumping and treating in the water treatment plant. And the last case can be compared with the picture above. We have a natural outflow through very shallow seepage outflows, and we collect the seeping water by gravel fields. So all the waters we collect, we need to treat, of course. Actually, we have 6 treatment facilities in operation with capacities between 200 and 1,500 cubic meter per hour. Last year, we treated a total annual volume of about 11.7 million cubic meter of mine water. So you can consider or imagine how many chemicals you need to add for the cleaning process. The main technology we apply is modified lime precipitation. It means pollutants such as metals and arsenic will be precipitated in iron hydroxide sludges. At one of our treatment facilities, we also have ion exchange technology in order to separate uranium. After cleaning the water, the remaining sludge needs to be separated from the clean water. It needs to be dried or dewatered as far as possible and to stabilized for long-term storage. In 2020, we had to manage about 12,000 cubic meter of sludge or precipitates from our water treatment plants. Finally, these sludges will be disposed in these kinds of special disposal cells. They are special containments with a base and a top ceiling and an additional final cover to avoid any infiltration of rainwater and outflow of contaminated seepage water. I come back to my previous slide, and now we want to focus on the right side, on the technologies which we need to regulate the water balance of our mining objects. I will try to explain these technology on our most challenging task of the dry in situ remediation of tailings ponds. In the upper right picture, you can see the initial situation of our largest tailings pond in the year 1993. You see large free ponding water bodies with extremely high contaminations. So the first step in remediation was the removal and treatment of this free ponding water and also of the poor water of the sludge. The second step was very difficult because it was not possible to simply move with technical machines onto the tailings because the sludge was extremely weak and extremely unstable because of water contents up to 95%. That's why we started to place an interim cover on the surface of the tailings, and we start from the outer rim of the pond and move forward to the center of the basin. This interim cover consists of so-called geotextiles and geogrids, and on these geotextiles and geogrids we placed a 1 meter thick soil layer to have a consolidation load on our tailings. The second or the next step is very time consuming, and tomorrow we have our very last installation of vertical trains. We installed these kinds of vertical trains in a raster of 5 × 5 meter all over the tailings pond. The drains reached depths down to 5 or 30 meters, depending on configuration. Through these drains, the poor water from the tailings could be squeezed out to the top and then drained on through a gravel layer into special pumping wells where we could lead the poor water to the water treatment plant. The next step after installation of the drains was the construction of a stable surface contour, so reshaping of the landscape. Because we want to avoid the infiltration of rainwater, we need to remove the former basin structure and replaced it by a spherical surface which consists of little hills and little valleys. You can see it in this map. Here are little hills, and the surface water or rainwater could easily flow from the area of our tailings pond. In some regions or in some areas of our tailings ponds, this contour layer had a thickness of up to 15 meters of soil material we had to add to this place. Last but not least, the entire area was covered by a final cover system. This was to minimize the infiltration and thus to reduce the contaminant release into the groundwater. So some general words to the cover systems. They serve as safe long-term storage of raised rocks and also tailings material on site. So we do not need to remove the material to our other location. The aim is always to minimize the contaminant release into ground and surface waters by reducing the seepage. On the right side, you can see a sketch of a multi-layer soil cover system we constructed especially on the tailings ponds. At the top layer, you have a recultivation layer, followed by a drainage layer. You have two different sealing layers, and then there is the several meter thick contour layer forming the new landscape. The cover systems have to achieve following functionality. They need to assure, they should reduce the radon and gamma exposure, especially in case of waste rock dumps. They should prevent wind-blown radioactive dust distribution. They should enable a revegetation, either as forest or meadow. And they should also provide a barrier to any misuse by people. To assure their functionality, institutional controls are required. This is mostly realized by an intensive monitoring program. And of course, these cover systems need to be maintained for longer times, especially in consideration of future climate change, more droughts, more flood events, higher risks of erosion. The next slide is only a very brief overview of our environmental monitoring of the water pathway. I don't want to go into detail. We have 1,400 monitoring points for ground, surface water, seepage, and also processing water. All these samples were analyzed for their chemical composition, radionuclides, non-radioactive parameters, etc. But we make also geomechanical investigations of soil samples with regard to the water content, porosity, or permeability. Wismut also runs various hydrometeorological stations where we measure precipitation, wind speed, and temperature. And you can see on this lower picture the construction of a large soil hydrological monitoring station. Here we can measure, beside soil moisture, also the percolation rates in different layers of our cover system. All monitoring takes place on different timescales. There is one kind of monitoring which starts long time before any remediation activity to characterize the initial site situation. And we have an project-related monitoring during the physical work. And after completion of our physical work, for example, the remediation of the dumps, there is an additional long-term monitoring necessary. So with this, I want to come to my conclusions. With regard to an efficient water management in mining, so the message to go, what should you do or consider in order to minimize the environmental impacts through mining? You should try to avoid any oxidation processes and also leaching and erosion processes by minimizing the water and oxygen entry into your rock material. Polluted and unpolluted water fluxes should be strictly separated because of reducing the effort of water treatment. Try to avoid and capture contaminated seepage water wherever it is possible. Underground mines are remediated in most cases by controlled flooding to have stable long-term conditions. And of course, the water storage and treatment capacities, they are strongly dependent on your local conditions, on your climate conditions, and of course also on your regulatory requirements. So what I can say, the understanding of the site hydrology, that means you have to identify the sources of pollution and the potential, is essential for the optimization of the remediation activities. And with this, I come to the last slide of my presentation. I try to give you some lessons learned with an overall view of our Wismut activity. The first point is you have to consider the life cycle approach. It means plan how to minimize environmental impacts before you start mining and not after. Try to avoid the mistakes which have been done in Germany in former times. Regulations imposed by authorities on the mine operators need to be defined, or you have to define the final state conditions with the regulation. Because if there are no limit values or target values, it's hard to plan any remediation activity. In this context, the tightening of regulatory limits can enhance the treatment efforts, because the lower the limit values you have to reach, the higher is the technical effort to clean your water, and you would like to save money, let's say. The aim of remediation is to achieve natural and stable systems which get along without any permanent technical measures. it means, for example, we want to avoid pumping until eternity. So, and last but not least, the accomplishment of a sustainable and low aftercare long-term solutions requires, on the one side, a careful weighing of ecological, economical, and social interests, the investment in robust technologies, and a comprehensive assessment of possible alternatives or alternative technologies. So with this, I want to end my presentation. Muchas gracias por su atención. Glück auf.
Muchas gracias, Dr. Seeland. De verdad, una exposición muy interesante y creo que da una impresión de la complejidad y del problema y también la complejidad de las soluciones que hay que darle a un tema tan complejo. Ahora tenemos un par de minutos para preguntas. He visto que hay una pregunta en el chat más general. Están preguntando si el plan de cierre de la Wismut es de acceso público y, de ser así, ¿dónde se puede descargar este estudio?
Was it the question? I have no translation, unfortunately.
Okay, so we'll give you the translation in German, okay? Die Frage war, ob der ganze Schließungsplan von der Wismut öffentlich zugänglich ist und wenn ja, wo man den im Internet finden kann.
Oh, sorry, it's... kannst du nochmal wiederholen, bitte? Sorry.
Ob der Schließungsplan der Wismut öffentlich zugänglich ist, und also die Studien, und wenn ja, wo man die herunterladen kann.
I would say it in English or German, doesn't matter.
No, in English.
I think these plans are not available on our website in public because it's too extensive. But if you have questions in detail, I'm pretty sure you can contact us and we can give you some extracts from this plan if you need some advice in certain conditions.
Okay, then we have this next question I will give in English because it's written in English. So Julio is asking, the safety fundamentals, principles of International Energy Atomic Agency, the IAEA, says that the introduction of new practices with radiations must be justified. Peru should do a study of justification before introduce the new practice of uranium mining and milling for avoiding the damage of uranium and its progeny.
Thank you very much for this interesting question. I would like to forward this question especially to my colleague, Dr. Schmidt, because he is our expert in relation with the IAEA. He is our senior expert who has a lot of experiences with IAEA. Peter, would you like to answer this question?
Yeah, of course. I would like to make it brief because time is running. Yeah, of course. Before we start any activity or before we start to develop documents for licensing, we perform measurements on the site and we perform an environmental impact assessment. And as a result of this environmental impact assessment, we conclude on the justification of remediation measures. And once the justification is given, then of course we identify the optimized remedial measures. So just the principles, justification, optimization, and limitation are an essential part of our considerations. Thank you.
Thank you very much. La siguiente y última pregunta es del Servicio Geológico de Perú y están preguntando ¿cuál fue la distancia promedio de dispersión de los elementos radioactivos en agua y suelos?
The average distance of the propagation of contaminants. Mm-hmm. It is not easy to answer because we have very different sites, very different regional conditions from hydrological perspective. and hydrogeological perspective. And in some, in the sandstone aquifer, for example, we have transport distances up to 5 kilometers downstream to the receiving water. And in case of our tailings management facilities, the biggest problem is not the vertical dispersion, but not the horizontal dispersion, but the vertical propagation into deeper aquifers. And so the area we need to monitor and to take care about in our remediation activities is quite huge around the actual mine. Several tens of square kilometers we have to monitor. And also the receiving waters were monitored up to 30, 40 kilometers downstream.
Okay, thank you very much. No, por el tiempo que tenemos, bueno, una última pregunta muy breve de Milagros Verástegui del Ministerio del Ambiente de Perú. Está preguntando, ¿el tiempo de post-tierra existe un plazo?
Can you hear me? Actually, yes. I already mentioned the time until we finally complete the physical remediation activities in 2028. But this is not in all sites. We have 2 or 3 sites which are already completed. But the monitoring lasts at least for 10 to about 15 years after the termination of remediation. So we have an aftercare responsibility to monitor the success of the remediation technology up to 10 years after finishing.
Thank you very much. Sí, bueno, han entrado más preguntas, pero por el tiempo tendría que cortar acá. Quizás si al final nos queda un poco de tiempo, podemos retomar una otra pregunta, quizás también son de interés para los otros panelistas. Entonces, por el momento, muchas gracias, Dr. Siland, ha sido muy interesante. Y bueno, entonces quisiera continuar con el siguiente panelista, el Dr. Ulf Barnekow. El Dr. Barnekow es geólogo, graduado en la Universidad de Göttingen y la Universidad Técnica RWTH Aachen, con experiencia especial en hidrogeología, ingeniería geológica y geotécnica. Y desde el año 1995 trabaja para la Wismut. Y desde el año 95 hasta el 98 como director de campo de ingeniería geotécnica, después como director de grupo de ingeniería geotécnica, remediación de sitios contaminados, y a partir del 2007 como jefe del departamento de remediación de minas. Y desde el año pasado es jefe de la división de ingeniería y protección contra la radiación. El señor Barnekow cuenta con más de 25 años de trabajo en el campo de ingeniería, especialmente en la rehabilitación de minas, incluyendo relaves, vertederos de roca estéril, minas a cielo abierto y emplazamientos mineros contaminados, con especial atención a la ingeniería geotécnica, la hidrogeología y la investigación de sitios, incluyendo estudios de viabilidad, etc. Desde el año 97 también ha realizado varios trabajos de consultoría internacional en sus campos de experiencia, por ejemplo para la Comisión Europea, pero también para el Organismo Internacional de Energía Atómica, la OIEA, y el Banco Mundial en países como Estonia, Europa del Este, Asia Central y Sudamérica. A partir de los años 90 también ha sido encargado como experto geotécnico del equipo de la Wismut responsable para el diseño técnico y la supervisión de la ejecución del proyecto multinacional de rehabilitación de la balsa de residuos de Sillamäe en Estonia, un proyecto de gran envergadura con costes totales alrededor de 20 millones de euros. This is Mr. Barnico, the stage is yours. Sie sind noch jetzt.
Okay, muchas gracias. Buenos días. I have to present in English, so at first I have to implement it here. Can you see it?
Yes.
Yes. Is it
correct?
Is it as a presentation of the whole screen?
Yes, it's a presentation mode.
And you can also see my mouse.
Yes.
Wait, here. Yeah. Okay. So I want to present you something about the remediation of the Ronneburg uranium mining area. It's a short review and some findings for mining legacies worldwide. Now I have to, here. Does it work? Okay. So my presentation is structured in 9 steps. I follow the follow-up of the remediation works. At first, I will give a short introduction. Then I will present the underground mine workings and their flooding. I will have some words on water treatment. Then the major part is relocation of waste rock dumps and backfilling of the open pit in Lichtenberg near Ronneburg. Then I will have some words on remediation of industrial sites in the area, some words about permitting procedures, and finally some words about the runoff diversion and flood prevention and the landscape management and after use. So you have already seen the location is here on the left-hand side, Ronneburg. The next city is the city of Gera. At that time, it was about 140,000 inhabitants. And the mine area is here nearby with the Ronneburg town. Today has about 5,000 inhabitants, and it's a densely settled area. So this gives you an impression. In 1990, the Ronneburg mining area was the largest mining area of Wismut. About 50% of the uranium was mined here. And to have an, no. Okay, and to give some, can you see it? Hello, can you see the mine?
Yes,
now it works. Okay, now it works.
It works, yeah.
Okay, so there's a mining legacy at Ronneburg with about 40 shafts, 22 levels in the underground. The maximum depth is about 900 meters below the level of 300 meters above surface. The area is 70 square kilometers, and the voids, open voids, are 25 million cubic meters. You see here the open pit Lichtenberg. It stitches into the mine and it is connected to the underground mine. It's about 160 hectares, and in 1990, about 50% of the pit was already backfilled. The contaminated areas is about was about 10 square kilometers. We had some 15 large waste rock dumps from the shafts and about 135 million cubic meters of waste rock. And so there were some environmental problems. One is, of course, from the mining itself, the radon from the ventilation shafts, the dust from the open surface, air exposed surfaces, and of course the water was contaminated, and we had some massive emissions of about 8 tons of uranium per year into the receiving streams. And here on the right hand side, this is the north, this is the south. There are 2 receiving streams here, 2 creeks, and another one here. The mine, okay, to have an impression, this is the situation in 1990. You see here on the left-hand side, this is the city of Ronneburg, immediately next to the slope of the open pit. The pit was about 240 meters deep, 2 kilometers long, 1 kilometer wide. And you see all these facilities here of the mines, the conical piles here. There were other piles here. So this is a large pile from the open pit here in front of us. So this was a situation at that time. The minefield itself, there were underground minefields. You see them here. This is the highway number 4. We separate between the southern minefield and the northern minefields. There are 3 minefields in the north, and they are hydraulically separated from the southern part of the mine. This is the location of the open pit Lichtenberg, and this is the city of Ronneburg. First step, of course, was securing measures in the underground. I will explain this on the next slide. So I already showed you the different underground minefields. Originally, they were connected to each other, but later we separated them by installing dams in the underground, in the tunnels. And this is a scheme from north to south. This is the southern mining area. You see the open pit Lichtenberg stitches into the underground mine, and we backfilled the entire pit with the waste rock dumps in the area and created a hill on top of the open pit. For securing the surface, we backfilled the upper levels of the mine to a level of, let's say, the uppermost about 60 meters below surface, completely by using a mixture of soil and cement and ashes from lignite burning. The lower parts of the mines, you see the levels here. Here we separated the different minefields in the underground so that they are now hydraulically separated. And so the water tables in the mine are different. Today, the catchment area is about 40 square kilometers. This means with an infiltration rate of 120 millimeters per year on average, you get something like 4.8 million cubic meters per year. During the mining period, it was about 1,200 cubic meters per hour. And today we have only about 300 cubic meters per hour. So the next slide, you see here, these are faults. And along this fault, there's also a hydraulic barrier. So the flooding strategy, after securing the uppermost levels against subsidence and securing the surface, and also after having clogged the boreholes over there, the flooding strategy was the long-term goal to achieve a water quality allowing for discharge into the receiving streams without water treatment. The midterm goal is to reduce the water treatment costs. And for the next years, we have to control the mine water table within a certain range to use temporary storage capacity when needed, with respect to the water quality control in the receiving creeks, and especially in the main receiving creek, the Weiße Elster River, because we have another mining area in the south, which also affects this main receiving stream for chemical reasons. The preferred option is to get a high mine water table. And the reason is that we have materials that produce acid. And we want to get calm hydraulic conditions in the underground mine and we want to put the acid producing volume of the rock and of the backfill below the water table in the mine. So therefore the idea is to get a high water table. We have, maybe I go back to the transparency before. This is the outflow point, the Gessen Creek Valley of this mining area. And there we have an horizontal drainage. We also have a pumping well here into the mine. And we have another second pumping well over here in order to be able, for safety reasons, to have a second possibility to control the mine water table. Yeah, so this is the flooding strategy. Water treatment, of course, the water has to be treated. The collected mine waters from the underground mine and also contaminated seepage from surfaces that are contaminated, for example, from the waste rock dumps or from their subsurface. The water treatment is plant today was erected in 2001 with a life period of minimum 25 years. It was just renovated in 2010-11 and just a few months ago as well. And this is a classic treatment scheme with lime addition. So we don't treat salts, we only treat heavy metals. I come later, I show this a little bit later. So this is the situation of the open pit Lichtenberg in 1990. You see the situation in 2005. At that time, the entire hole was backfilled, and later we created a new contour on top because we had more materials from the waste rock dumps. We used these heavy lorries here at that time. The quality of the seepage water from the waste rocks was also different. We had acid producing material, and we also had a neutral drainage. Both could have a significant uranium here, but in the acid mine drainage we also find nickel and other metals. So this water cannot or has to be treated before being discharged. The waste rock management, so the remediation of the Ronneburg mining area was a joint remediation of the waste rock dumps together with the open pit Lichtenberg. We had to care for the different chemical compositions of the material, and so therefore we decided to remove all these waste rock dumps into the open pit. And all the waste rock dumps north of the highway, we couldn't transport them across the highway. This was quite a problem. So therefore we created a new waste rock dump over here where we put everything together north of the highway. So the preferred option of the remediation strategy for the relocation of the waste rock dumps, the open pit had to be backfilled because we had unstable slopes next to the city of Ronneburg. So it was clear we need some backfill up to the natural surface. And the relocation became the preferred option for most of the waste rock dumps south of the highway because it fulfills the principle to concentrate the contaminants and results in reduced aftercare costs. The surface becomes smaller. It grants the lowest emissions into groundwater body because it stitches into the mine. It is also connected with the water treatment and collection of the mine itself. And it grants equal or lower costs to the long term, and it meets the principle of sustainability. For this, we had to investigate the chemical composition of the waste rock dump material, and we classified the material into 3 different types. The so-called acid-producing material, the red one, a less acid-producing material, the yellow one, and the neutral material, the uppermost one. And then we put in the most acid-producing material in a level below the future groundwater table in order to reduce oxidation. And the red material was also added with lime. You see in the next, no, does it work? Yes. Here you see the operational procedure. You see the different zones, A, B, and C. So it was a classified excavation and placement in the open pit. The layers were compacted, and we added with a big dozer lime on top in thin layers. And then we compacted layer-wise with the beginning 60 centimeters, later 90 centimeter layers, and added lime in there. You must imagine that this backfill body is directly connected with the underground mine. We had tunnels that were connected directly to the open pit. The reason for the pit, to start the pit, was the high marcasite and pyrite content and the organics that and the organic matter that led to burning, to fires in the mine with burning material. And also the waste rock dumps were very hot. We had up to several hundred degrees Celsius in some parts of the waste rock dumps. So the southern part of the Ronneburg area, all this material was put into the open pit. And in the northern part, we concentrated it in the Berwalde waste rock dump. And of course, after having placed the material there, we have to reshape the slope for long-term stability. We have to cover it with mineral soil, and we need vegetation to avoid erosion. And then we construct access roads and ditches to divert the runoff from the surface. Together with the backfill of the open pit, we had a co-disposal of other materials from the different type of remediation work. Total amount about 4 million cubic meters of contaminated debris, scrap metal, contaminated soil, sludges from settling ponds, demolition materials, the excavated material from industrial areas and footprint areas of relocated dumps, landfill material. There were landfills in the waste rock dumps, and we need some specific compaction measures to get the permit to put it into the open pit. We treated some organic soils that were contaminated with organics, with hydrocarbons in a biological treatment plant. And of course, we had about 1.2 million cubic meter of contaminated ashes from lignite burning. This material was used for water treatment during the operational phase. And at least we also constructed a waste depository for residues from the Ronneburg water treatment plant inside the open pit and covered it as well, together with the complete remediation. These are some impressions about the 3 sites north of the highway number 4, the situation in 91. You see the industrial sites and the waste rock dumps and the shafts. And the next slide shows then the situation in 2013. At that time, all the material was relocated to the Beerwalde waste rock dump. And we placed a soil cover consisting of 2 layers on top of this waste rock dump in order to reduce the infiltration rate to no more than 5% of the annual precipitation. The annual precipitation rate is something about 750 millimeters, and the infiltration rate is about 120 millimeters. And due to the tight sealing layer at the lower part of this 2-layer cover system, we further reduce the infiltration here. Industrial sites, remediation of industrial sites, of course, dismantling and demolition with respect to radiological safety. This is also of specific importance for milling sites and processing plants. Sorting of different types of waste and separate disposal. We recycle steel where possible. Radioactively contaminated waste rock materials, soils and other such type of materials were relocated into the open pit, if needed with special compaction measures. Uncontaminated materials were recycled. Mixed contaminated soils with radioactive and or hydrocarbon contaminations were treated in biological treatment plant, or they were disposed in the hazardous waste depository Lichtenberg, about 1 million cubic meter of material. So we have also such a waste depository there constructed. In the end, everything is covered and recultivated with recultivation soil, and where necessary, and we need a vegetation for erosion control. The permitting procedures maybe will be more explained in more detail by Peter Schmidt, especially regarding the radioactive aspects. Of course, we need, according to mining law, we needed, or we had an operational closure plan, and this was permitted. And for each individual measure within the remediation, we needed individual closure operational plans. Under water law, we needed a permit to use the waste rock and to put it into the open pit. And according to radiation protection law, I think this will be explained by Peter Schmidt in much more detail. So if needed, we come back there later. Maybe regarding the radioactive effects there, during the ongoing operational period, of course, the people living just in the surrounding were affected by dust, by the lorries, by dirt from the activities, by the radon from ventilation shafts, and of course the water maybe was also a big problem, but at that time the main problems were the let's say the quality of water regarding the industry production in the downstream area. The main permitting procedure for the open pit, we needed a planning approval procedure to construct the final contour, to place a cover and vegetate it. We had preparations for after use of the areas, including landscaping, and we needed to catch the surface runoff and divert the water to the receiving streams, including flood prevention measures. This shows the situation in 2009, and you see here the main receiving stream. This is the deepest point, 240 meters above sea level. The highest point is 370 meters above sea level. The average level here is 300 meters above sea level. Here is the main outflow point of the mine. Here's the well number 6, and here is the well number 2, and also we have the water treatment plant here. You see the subsurface of the former waste rock dumps, and here we constructed a runoff retention pond in order to prevent the Runnebook city against a flood from the runoff here. So there is this open pit here is now this here, and this is all the waste rock dumps here in the surrounding are now inside the open pit. The surface, there were landscape management plans for the surface.
Mr. Vaneco,
yeah,
you should come to an end.
Yes, okay. I'm in 2 minutes. I'm finished in 2 minutes. You see the different. The dark green is a forest. Most of the surface is forest, and the other yellow or bright green areas are areas that can develop forest or that will stay as open grassland. So. Long-term tasks after remediation, of course, maintenance and repair of covers, roads, ditches, and the needed facilities, and the management of the sites, the collection and treatment of decant mine water and of contaminant seepage. The maintenance of open underground mine workings are not relevant in Runnebook anymore. Of course, we need an environmental monitoring. We need to secure the surface, and of course, we need documentation and knowledge management. And so my last transparency findings for the mining legacies worldwide: prepare overall mining projects as well as the individual mining operational plans with respect to mine closure works and costs at any time. For this, proper conceptual site models are needed for planning, and an appropriate risk management and assessment and management is needed. Involve affected stakeholders. Reduce the need for remediation during and after operational phase by proper planning, steering, and documentation of the operation, and as well as of the remediation. Care for implementation of proper monitoring and control regimes, both by the operator and by the responsible authorities, with clearly defined responsibilities of all involved parties. And care and pay for qualified and experienced personnel and for proper equipment at any time. Thank you very much. Okay.
Muchas gracias, señor Vaneco. Muy interesante. Hemos visto otros aspectos relacionados al cierre de estos tipos de minas. Y tenemos por el momento 2 preguntas, pero si quedan más, todavía tenemos 2 minutos para agregar otras preguntas. Bueno, la primera es una pregunta más general. Están preguntando cuánto es el costo total presupuestado para la remediación de la Wismut.
Yeah. The overall remediation costs were fixed in 1990 by law to be about 6.7 billion euros. Today we are, I think, at a limit of about 8 billion euros. The annual budget of Wismut is about 120 million euros. We have about 800 people working with Wismut. About half of them are workers. The remediation of the Runnebook site is maybe in total around about 2 billion euros, 2 billion. So it's a really large amount. And you must imagine that this is, you can see it as a, let's say, collateral damage from the Second World War. This became under Russian control, and so the people, they had no chance. They were just removed, and then the mining started there. Yeah. So it was measure to have the people still there, yeah, not to leave all the people out of the area. It's densely settled, yeah, and it has to be developed again. And so there was, let's say, a period in 1990 when the money was there to make this decision. Yeah.
Thank you very much. La segunda pregunta de Eddie. ¿Cómo obtuvieron la cobertura orgánica para la remediación de los depósitos de residuos? Y la segunda parte de la pregunta es, ¿se continúa monitoreando los niveles de radiación hasta la fecha y a cargo de quién?
Maybe Peter Schmidt shall answer regarding radiation question aspects. Of course, there is this is another presentation, the monitoring of the different pathways. So I think this is maybe too much to explain here. It takes more time. Of course, we have to, today the main problem is water, but during the operational period, dust and dirt and especially also radon could be a problem. It also depends on the site where we are. In the mountain, ore mountains, sometimes we often have problems with radon. Here, the problem was dust and water quality, and also geotechnical safety was a big problem. Yeah.
Okay, muchas gracias.
Yeah.
Bueno, entonces podemos continuar. Muchas gracias, señor Bánico. Voy a continuar con el siguiente panelista, el doctor Peter Schmidt. El doctor Schmidt estudió física y cuenta con un doctorado en el campo de física de la salud de la Universidad Técnica de Dresden, en Alemania. En los años 80 ha hecho trabajos científicos en la Universidad de Dresden sobre dosimetría de neutrones gamma, dosimetría cósmica a bordo de naves espaciales, dentro del programa Intercosmos, con experimentos en el JINR de Dubna, Rusia. Además tiene experiencia laboral en Suiza, en Ginebra. También se dedicó como jefe técnico de Comet Technik AG en Suiza, en Berna. Y desde los años 90, desde el año 95, trabaja para la Wismut. Y desde el año 2001 como jefe del Departamento de Vigilancia y Protección Radiológica. Y él cuenta con más de 35 años de trabajo científico y de ingeniería en los campos de la dosimetría de las radiaciones, la evaluación de los riesgos radiológicos, la medición y evaluación del radon y la vigilancia del medio ambiente. Desde el año 97 también ejerce actividades de consultoría internacional en sus campos de experiencia, también para la Comisión Europea, la OIEA y el Banco Mundial, también en Europa Oriental, en Rusia, Asia Central, África y Sudamérica. Muchas gracias, señor Schmidt, por su presencia y la palabra es suya.
So thank you very much for the kind introduction. I'm trying to open my screen here. Is it okay? Can you see my?
You have to bring it to the presentation mode. It's still in the editation. Yes, now we see it perfect.
Okay, good. Good morning once more, dear colleagues, ladies and gentlemen on the other side of the ocean. It's a pleasure for me to talk about the radiological aspects of mining and milling of radioactive ores, and I have also a very short contributions regarding the need to involve stakeholders. I have structured my presentation as follows. In the beginning, I would like to say a few words regarding radioactivity, the effective dose, etc., because I guess not everybody is aware of these very special topics of radiation protection. I will talk about the radiation protection principles for planet exposure situations, and then demonstrate some analysis results of our exposure considerations, what we measure at the sites regarding exposure of workers and also the local public. And as mentioned already, 3 slides at the end regarding stakeholder involvement. So a very, very brief introduction what radioactivity is. Perhaps you know that we have radioactivity, natural radioactivity everywhere around us. We have it in the soil, we have it in air, we have it in the wall, in the ceiling, everywhere. And this is because some of the radionuclides have a very long half-time and they decay very slowly. And one of these elements is uranium. Here we see the uranium decay change with a number of daughter nuclides, which again decay, and we see a very important nuclide. This is the radium, because by the decay of radium, radon is built. Radon again is a noble gas, and it's very important with respect to exposure at mining sites. The unity of activity is 1 per second. It's also called 1 becquerel. Becquerel, a French scientist who discovered the radioactivity in 1894 already. And when we relate the activity to a mass unit, then we speak about the specific activity given in units of becquerel per gram. So radioactivity and radiation can build doses in the human body. We have 2 options. The first is the exposure by external radiation. This is gamma radiation and electromagnetic wave radiation, comparable with cosmic radiation, or also comparable with the X-rays we received during medical investigations. This electromagnetic wave penetrate into our body and give energy to the body over, and by this radiation dose is built. The other option is that radioactivity is incorporated by inhalation or by ingestion. These are mainly particles onto which the radionuclides are bound. I mentioned already the noble gas radon, which may be inhaled, but this radon has also very dangerous daughter nuclides, which create high doses, in particular in the lung, and may cause lung cancer. With the goal to compare different kind of interactions of radiation, the effective dose was defined. The effective dose allows to compare different radiation and their interaction with the human tissue, and is a measure for the radiation risk. The unit of the effective dose is sievert. Sievert, this was a Swedish radiologist, biologist also, but normally we use the unit millisievert. This is 1,000th of the sievert, because millisievert is a level which we normally observe in the nature. The natural background in Germany, for instance, is up to 2 to 5 millisievert per year for the population, whereby half of this value is attributable to the radon. In Peru, I would expect that the natural background is a little bit higher, because the elevation of the location of many cities of the big part of the country is very high. So the higher you come, the higher is the contribution of cosmic radiation to the natural background. But once more, please have in mind for the following: 2 to 5 millisievert is a good level or a good number for the natural radiation background. And then, of course, the question comes up: at what point is ore radioactive ore? Once more, we have the radioactivity everywhere, and we have uranium in the Earth's crust as an element. The mean concentration in the Earth's crust is 3 to 4 ppm, particles per million. Just to give you an idea, if you have an area 1 kilometer by 1 kilometer and only 30 centimeters in depth, this soil layer contains 1.5 tons of uranium. I guess nobody would expect that. Then we can ppm uranium transfer into the unit of activity. 1 ppm uranium is equal to 12.3 millibecquerel per gram uranium-238. And now the International Atomic Energy Agency, and I guess Peru is also a member of the IAEA, the guys have defined as a clearance level for each radionuclide in the uranium and thorium decay chain, the value 1 becquerel per gram. So with other words, 1 becquerel per gram, this is roughly 80 ppm uranium. And the consequence is, whenever you dig ore with more than 80 ppm uranium, then this is radioactive ore and it is considered as norm, naturally occurring radioactive materials. And handling of norm requires radiation protection measures and requires the application of a regulatory framework for the treatment of norm. A last very theoretical slide. This is radiation protection principles for plant exposure situations. As mentioned already in one of the questions before, the International Commission on Radiological Protection distinguished the following situations. Planet exposure situations. This is your case. You want to start a new mining activity, so you plan to do it. In contrast to that, at Wismut, we have to deal with legacies, with the remediation, and it was an existing exposure situation already when we started. And the third situation, this is Fukushima, Chernobyl, emergency situations, but of course, this is out of this presentation. The main principles which we have to apply in radiation protection, this is justification, optimization, and limitation. And limitation in plant exposure situations requires to keep the standards 1 millisievert per calendar year effective doses for members of the public, in addition to the natural background. So once more back to the question which was given already before. When we start in doing something, then we perform an exposure analysis. And when we identify effective doses for the public higher than 1 millisievert, then there is the need, there is the justification for remediation. And there is another number which one has to know. This is 20 millisievert per year effective dose for occupational exposed workers. So with other words, when you plan to open a new mining activity or new mine, then and the ore has more than 80 ppm uranium, then you need to apply the national regulations for radiation protections and for norm. I do not know how these regulations are developed in your country, but I'm pretty sure you have something in this regard. You have to perform environmental impact assessment. You have to monitor the exposure of works. You have to develop and conduct an environmental monitoring. I myself, I'm responsible for monitoring in my company. Back to the questions of before. Yes, we have a permanent monitoring at the sites, including at the moment 1,200 groundwater investigation wells, 300 points where we investigate surface waters, and 350 points where we investigate the quality of air. And this monitoring is done by Wismut, but it is also approved by the authorities. What you further have to do is to minimize and control the dispersion of radioactivity. What you see here in one of these figures, this is we permanently spray water on haulage roads to minimize the development of dust. You have the need to develop a waste minimization and waste management program for mine waste in general, and in particular in this case for radioactive waste. And whenever you have radioactivity playing a role, then you need to involve stakeholders. But this is not only, this is in general so in mining. What does it mean, exposure analysis? So we have on the one side, we measure the radioactivity in the environmental media, air, soil, and water, and then we follow the paths of the radioactivity into the human body. It's better shown in this slide. For instance, dust is whirled up from a waste rock pile, dust falls down or is washed out by rainfall. It goes on the surface of crops. Crops are taken up by cattle. The cattle give milk and meat. Milk and meat is consumed by a mother, and the mother gives this radioactivity further with the mother milk to the child. This is the most complicated exposure pathway which we consider. Here are some typical results, and shown is the exposure of workers in the upper case for underground work, and what you can see is that the doses here reach levels of 4-5 millisievert per year, so we are still below this 20 millisievert per year, which is the limit. This is due to the excellent ventilation system we operate in all our mines in the underground. For work on the surface, the doses are rather low, so our workers receive, as a rule, 1 millisievert, not more. And again, this is very low in comparison to the 20 millisievert limit for workers. Exposure of the local public. This is a picture showing two tailings ponds, and in the between these ponds we have a small river, and in this river we measure radium, we measure uranium, we have lead, we have polonium and other radionuclides. And in this case also we perform the exposure analysis, and what we received here as a result is that for the child the dose can be higher than 1 millisievert per year, and is for the very conservative scenario that the water is used as drinking water for babies and also for the preparation of baby food. This is of course conservative, but we have to consider it according to regulations and also guidelines for the performance of exposure analysis, which exists in Germany. And this is a quite other situation, a picture of the Schlema site. Here we have the situation that on the door of a very, very big waste rock pile, there is a residential area. This is before we started with remediation. Meanwhile, this waste rock pile is covered, but we still have elevated concentrations here in these houses. And you see that the exposure or the effective dose goes up to 4 millisievert per year. And this is, of course, clearly above 1 millisievert per year. And the reason, and the reason that we have to cover it. Okay, a very short excursion in the question of stakeholder involvement. And I remember I was 12 years ago, I was invited by the IAEA to participate in a workshop in Argentina with a lot of participants from Latin America. And we discussed questions of how to include stakeholders because you cannot do any mining activity now, you cannot open a new mine without involvement of those who have a clear interest that their concerns are properly considered. So stakeholders are operators, regulators, the local public, municipalities, donors, etc. Our strategy at Wismut was always to play with open cards, to be open, to show all the environmental data, to involve the local public in decision making, to have an public relation policy, and to preserve mining traditions. By the way, in 2019, the Wismut sites became part of the UNESCO World Cultural Heritage Erzgebirge crucial mining region. You have to take care that you, with your activities, develop the local workforce. And then the most important in stakeholder involvement is to return the sites to productive reuse in line with regional development plans and stakeholder interests. For illustration, to show you some pictures, building bridges with the public. So we inform the local public. We organize every year open house days with a lot of visitors. They can look into the mine. We opened 2007 already exhibition hall at the Ronneburg site where the history, but also the progress of remediation at the Wismut site is demonstrated. I myself, I'm a runner. I like to participate every year at the Haltenlauf. This is a run over a remediated waste rock pile. We perform international mining symposium every 3 years. And once more, we take care for the mining traditions in the region. By the way, I'm very often invited by the IAEA and by other organizations to demonstrate the progress of Wismut. And at this point, building bridges with the public, this is perhaps one of the biggest stories of success which we can demonstrate in the public worldwide. So with that, I'm coming to the end already. Thank you very much for your kind attention, and I kept in time, and it would be nice if there are one or two questions. Thank you.
Muchas gracias, señor Schmidt. Muy interesante su presentación. Ahora tenemos un par de minutos para preguntas. Por el momento no veo ninguna en el chat. Siéntense libre a agregar algo. Si no, quedó pendiente una pregunta de antes, que quizás ahora también puede responder el señor Schmidt. Está preguntando qué concentraciones de uranio en aire, suelo y agua ya se considera contaminante. Creo que ya su exposición lo implicó, pero quizás lo podría destacar un poco más a detalle.
Yeah, of course. No, I didn't mention that. But uranium in water at first. Clearly said as it is, uranium is much more chemotoxic than radiotoxic. That means the limits for uranium in water are more driven by the chemical hazardous interaction of this element with the human body, in particular with the kidney. That is why we have the UNESCO, not the UNESCO, the WHO, World Health Organization, recommends a value of 30 microgram per liter as maximum admissible concentration in drinking water. We have in Germany a standard of 10 microsievert per liter, and I know also in the US the level is 15 microgram per level. But once more, this level is driven by the chemotoxicity. With respect to other nuclides, of course, for radium, we want to have not more than 0.2 becquerel per liter in water. In the air, uranium is not of concern. It's more, the long-lived alpha emitters in dust, but we consider 20 millibecquerel per cubic meter as a level which is still normal. And then very important are the figures for radon. And here we have a reference value of 300 becquerel per cubic meter in the atmosphere. But once more, on the base of this exposure analysis, we can derive for each radionuclides for certain scenarios such limiting values.
Muchas gracias. Tenemos una consulta del Servicio Geológico de Perú que está preguntando ¿cuál es la metodología de monitoreo o muestreo para determinar el nivel de exposición radioactiva en las personas en las poblaciones cercanas?
Monitoring deserves a presentation for itself. But anyway, we have different types of monitoring. We have a so-called baseline, basic monitoring. This is a monitoring of air and water investigation points spread over the whole area. And here we want to detect the impact on the people living on the sites. But then we have, of course, monitoring points which serve to investigate the impact of an individual object and also the impact of remediation works itself. For instance, when we relocate a waste rock pile, then dust is whirled up. So we install dust investigation points close to the site and also on the fence to the environment outside of Wismut. This is one of the principles. It goes on. Once we have finished the remediation, and we have it already at some sites, then we install a post-remedial monitoring, which is dedicated to demonstrate the success of the remediation. And this is fed into a long-term monitoring, and we know that we have to do this monitoring at the sites, the long-term monitoring, even 30 or 50 years after the termination of the physical work.
Gracias. Una pregunta es sobre la cadena de decaimiento del uranio. Y están preguntando si los 13 hijos del uranio son más peligrosos que el propio uranio.
Yeah, that is true. It also always depends on the interaction of these radionuclides when they come into the human body. Once more, I mentioned radon is a noble gas, and when you inhale it, it is also exhausted within a very short period. But together with the radon, you inhale also the daughter nuclides of radon. This is polonium, Wismut 2018, lead 2014, 2018, etc. And these small radionuclides, they are bound to aerosols and bound to dust. And they are fixed in the upper part of the breathing tract and in the lung. And these radionuclides are much more dangerous than the uranium because they give their energy very local to the whole human tissue, and this may cause lung cancer. We have for each radionuclide a so-called dose conversion factor. This is the dose by intake of a certain amount of radioactivity, and these factors are nuclide specific and they differ by 2 orders of magnitude. By the way, the most dangerous radionuclide is actinium-227 from the uranium-235 decay chain. Sorry for this Latin.
Muchas gracias. Una consulta adicional a la metodología del muestreo. Ya dijo que podría ser una exposición entera, pero quizás muy brevemente. La consulta es si aparte del muestreo de componentes ambientales como suelo, aire, agua, polvos, también se hace un monitoreo epidemiológico en las personas que viven cerca de las zonas contaminadas.
No, we don't. A clear answer. Because we know that the level of exposure at the sites is in the order of a few millisievert. Biological monitoring or monitoring of human tissues, for instance, you can look for the blood aberrations, changes of blood or so. This occurs only at much higher doses in the order of 100, 200 millisievert, where you can really see the impact of the dose on the human tissue. But at the level we are working at, such biological effects cannot be seen. I know that in the beginning of the Wismut project, there were some investigations of urine and also of blood, but clear relations were not found.
Okay. Tenemos una pregunta más sobre la parte legal. Están preguntando si existe en Alemania un marco legal especial para la minería de uranio o si eso se encuentra dentro del marco legal de una mina convencional o minería convencional. De ser especial, podría citar el marco legal.
No. We have, of course, radiation protection regulations specially dedicated to the problems of uranium mining and milling. And this is a funny story. Germany, maybe you know, we became unified in 1990, though the Wismut sites are located in East Germany, the former socialist or communist or Soviet Germany. And when it came to the unification of Germany, the western part, the big part, was not prepared because there was no uranium mining and milling. And that is why in the first 30 years, really until the last year, we applied the radiation protection regulations of the former German Democratic Republic because these regulations included a special part especially for uranium mining and milling. Meanwhile, we have adopted in Germany a new law, radiation protection law, and also a new ordinance, and there are special chapters for radioactive legacies, and we fall with this under these regulations.
Okay, la siguiente pregunta es del Ministerio de Energía y Minas de Perú, en inglés, por eso lo voy a leer en inglés. How many years of data collection is recommended for an environmental line base for a new mining project?
So, sorry, I could not understand the first part.
How many years of data collection is recommended for an environmental line base?
How many years of data collection?
Data.
Ach, data collection. Ah, data. Sorry. You mean when we start a remediation and we have to perform the environmental impact assessment of the existing exposure situation, then as a minimum we have to perform monitoring for 1 year. This is it comes from the water regulations to characterize a water course with regard to its contamination. You need to have measurements over a year, and the same is also with radon. radon undergoes seasonal deviations, so we have to do a minimum winter measurement and a summer measurement. Yeah, but normally for big objects like the relocation of the dumps into the open pit, which what my colleague Ulf Barnekow showed, it took years, 5-8 years, to have all the data compiled, to have enough information for development of the optimized remediation measures.
Maybe I would like to add that in 1990, of course, there was already some kind of monitoring or some monitoring during operational phase, but it was a given situation at that time, and so we started immediately with securing measures, and at the same time we started with the investigation program, and this needed, I would say, 3 or 4 years until the base line data were prepared and available to make decisions and to start with the first objects of the most emergent objects or most urgent objects. Yeah, thank you.
Yo creo que la pregunta iba más a cómo determinar la línea base, por ejemplo, para el nivel de fondo de radiación en Perú antes que comience un proyecto nuevo. Porque el señor Schmidt mencionó que en Alemania tenemos un nivel de fondo de, no sé, me acuerdo, 3 a 4 milisievert por día, y en Perú no se sabe, ¿no? Todavía, para determinar esta línea base. Eso creo que era la pregunta.
My answer would be as follows. I mean, once more, we have another situation, or we had another situation. This was an existing situation. You plan to do something new. So what you have to do, and this is an international standard, before you start your mining activity, you have to investigate the current environmental situation on the site. This is done in the form of so-called baseline monitoring, because at the end of the mining activity, you have the goal to come back to the situation as it was before. This will not succeed to 100%, but you need to have some information. It makes no sense to remediate the nature, to go deeper as it was before mining. That is why baseline monitoring before you start is a must.
It is also a process. It starts with a lot of lack of data, and it becomes more and more detailed. And then you pick out, or you find the problems, and then you start to go in more detail. And maybe some additional information regarding the long time period of the remediation of Wismut. Of course, from 1990 on, we had a certain budget per year. And so, of course, we could only do what we could do with the staff and with the money. And so, therefore, some of the objects, like, for example, tailings ponds, came or started later. Because we just needed, and there we had time to develop or to investigate in more detail. So it is always some kind of optimization. I start in Ronneburg, for example, with the underground mine, with securing measures of the surface, with the separation of the minefields, and then I start with the waste rock dump remediation and others. So step by step, because it was too large to do all at the same time. In many projects in the world, you see large mining projects where they think they can finish the remediation within 3 years, and but this is not realistic.
Muchas gracias. Bueno, considerando el tiempo, lastimosamente ya tenemos que llegar a un fin. Entiendo que es muy difícil resumir el... Stop. ¿Alguien dijo stop? Bueno, voy a continuar. es un desafío resumir el trabajo de 30 años en solamente 2 horas, ¿no? Entonces, probablemente quedaron algunas preguntas abiertas. Sin embargo, me queda nada para primero agradecer también a los panelistas, y creo que ha sido un seminario que logró tocar algunos temas puntuales, pero también logró dar una visión general de la complejidad que involucra la remediación de una antigua mina de uranio en base de la experiencia de la Wismut, que tiene muchos aspectos a considerar. Hemos profundizado un poco el tema del tratamiento del agua, sobre todo del agua subterránea. También hemos visto la complejidad de cerrar los componentes mineros como los tajos y las minas subterráneas o los socavones subterráneas. También hemos visto la complejidad de manejar los residuos peligrosos que se generan, tanto de contaminación, digamos, convencional, pero también los desafíos que se plantean adicionalmente por la presencia de contaminaciones radioactivas, ¿no? Que es un tema muy aparte que requiere un manejo especial, y creo que también hemos visto hoy que es tampoco un tema que se puede abordar tan sencillamente, y entonces también ese tipo de consideraciones son importantes, no solamente para el caso que hemos visto hoy de una situación que se encontró en el año 90 con la presencia de pasivos y una contaminación existente, sino también en vista a posibles futuros proyectos con la finalidad de evitar que se repitan errores o que se generan situaciones como la de la Wismut en los años 90, que requieren esfuerzos mucho mayores, incluyendo también altísimos costos. Hemos escuchado que el proyecto hasta la fecha ha costado como 8.000 millones de euros de inversión, que al final del día ha sido dinero público de los tribuyentes alemanes. Y también hemos visto que importante es que estos proyectos no solamente ven la parte técnica, que es muy complejo por sí mismo, sino también esas minas no se encuentran en un espacio vacío, sino están dentro de una zona habitada. Entonces, el involucramiento de la población local, de los diferentes stakeholders, ha sido clave tanto en ese proyecto como en otros. Entonces, no solamente la remediación de los pasivos, la eliminación de los riesgos asociados a la contaminación y la radiación ha sido un desafío, sino también el reconvertir en esas zonas en espacios que dan calidad de vida a las personas y también generan nuevas oportunidades recreativas, pero también laborales para las personas que viven en cercanía de estos espacios. Eso quedaría para mí como un breve resumen. Nuevamente, muchas gracias. Y ahora, Jan Patrick, te doy la palabra para el cierre del evento. Muchas gracias a todos.
Ya, muchas gracias, Achim, por la excelente moderación. Muchas gracias a nuestros expertos, Peter Schmidt, Ulf Barnekow, Robert Sieland, por las presentaciones súper interesantes y también por contestar todas las preguntas. Muchas gracias a Alfredo Rodríguez, director general de Minería, por estar acá, también acompañado por parte de su equipo, la directora general de Calidad Ambiental, Milagros Verástegui, del Ministerio de Ambiente, también ha estado acá. No la había mencionado al principio, no la había visto en la lista, lo siento. A todos los participantes, muchas gracias por estar acá. Y yo creo que lo que acá podemos tomar es hay experiencia, hay know-how en Alemania en ese tema que quizás no todos tenían así presente, que hay ese know-how. Lo que no se tocó ahora, pero tengo entendido que Wismut también ha trabajado con otros países, así que si tienen más interés en conocer, o sea, pueden contactarlos en las presentaciones que les vamos a hacer llegar como PDF. A posterior de ese evento están los contactos de nuestros expertos y obviamente pueden contactarlos si hay todavía preguntas en detalle. eso ha sido nuestro último evento dentro de nuestro proyecto de cierre de minas financiado por el Ministerio de Economía de Alemania. Vamos a tener fin de mes todavía nuestro cierre de proyecto, que también están cordialmente invitados. Y ya, me queda nomás desearles a todos un excelente día en esos tiempos complicados. Por favor, manténganse sanos todos. Y bueno, la próxima, cuando ya otra vez tengamos eventos presenciales, sí hay cafecito y unos bocaditos. Lamentablemente, para los eventos virtuales todavía no hemos encontrado una solución para compensar ese tema culinario. Muchas gracias a todos por su presencia, por su participación, y también más adelante como Cámara Alemana y el Centro de Negocios Mineros estamos a su disposición. Que tengan un excelente día. Muchas gracias.